recording. Okay, I'm recording. Great. Okay, this is linear regression part two. Before I start, are there any questions about the last lecture or the assignment? Okay, pretty clear what to do. So today, what I'll be showing you is more of the nuts and bolts on actually how to design a regression model. So how do you actually go about appraising your data, selecting your exposure outcome variables, selecting your confounders, selecting your predictors, mediators, and also how to test those variables, the theory behind how we go about selecting variables. We'll talk about how to actually test whether or not a variable is impactful in a model. So should you include different covariates? What's the effect of removing one and so forth? Okay, so last week was more introduction. To this week we go more into depth with linear regression. And depending on where we are, I think because I expect some package compilation problems that we should probably just cover this today, but if we finish early, we may start to get into logistic regression at the end. But I think this one is a bit longer. Usually there's more questions. Okay. And just let me know if you can't see anything because it's easier for me to face this way. So just tell me if it can't see. Okay, so this is recap from last week. So when we gather data for human research, multiple variables are often gathered, and the variables can serve diverse roles, being outcome exposures, confounders, or predictors, or interaction terms, even. Statistical models are the framework under which these variables are synthesized to derive meaningful interpretations. So, again, recap of last week, explanatory models and predictive models. Does anyone remember what the main difference is between the two? Like if I said to you, what's the elevator pitch, like the one sentence? So which one is concerned with the next patient? One? Predictive, right. So predictive is trying to predict a patient out of the sample or in the sample, but the next patient that you see in your clinic or in front of you or wherever you're seeing them or whatever's happening. Explanatory, to explain an existing set of data, to explain an existing clinical etiology or concept or idea. Okay. So explanatory models look at the association between one or multiple exposures and an outcome while adjusting for other variables that are not the primary focus. And predictive aims to provide an accurate prediction of an outcome based on a set of explanatory variables without a particular emphasis on understanding the underlying relationships. So I guess before we start, what are the different ways of how would you, if you're starting a study or if you are working on a study, what are the different kind of ways of variable selection? Does anyone have an example of how they might select variables in the study? So let's say you're designing a study. How do you choose which studies to which variables to include in your research? Yes, that's a great exactly. So start with literature review, of course. So see what others have done and see what are the maybe outstanding questions. So that's a great start. Uh, what else might you do? So what's already been written, and then what else might inform you? So you're all going to be working with clinicians or in wet labs, right? Presumably, or in research labs. So the problems that are facing the researchers day to day, the clinical problems that they may seek answers to, these can motivate your variable selection. So if you're constantly, for example, I can think of in rheumatology, we're constantly seeing delays in time to medication. So time to medication became one of the variables included in the cohort study that we designed. So the clinical um, gaps in care may inform your variable selection as well. So practical on the ground experience may inform what variables you want to include. And what's the kind of third thing that we usually think about with variable selection? I'll give you a hint. We just spoke about it. Our goals, right? So depending on whether we want to explain or predict, it may inform how many variables we collect. Uh, okay, and then this is more operational, but um, what's kind of the other what's one of the limiting factors in how many variables we can collect? So the more you collect, the more it costs, usually, right? The longer a questionnaire for a patient, the longer a telephone interviewer has to spend asking people questions, the more data you collect, the more it costs. So there's always pragmatic limitations of how much data you can collect based on cost, based on your scope, how much human resources you have, and how much technical resources you have. So that's the other thing too. So you may prioritize variables based on available resource. And the I guess fifth thing is your approach. So do you want to take all the variables available and frame no hypothesis and just plug in everything that you have? Or are you coming in with a predefined a priori, which means before you ask the question, you already have your hypothesis and you want to test a specific hypothesis, you may have a narrower set of variables. So that's kind of just a brief overview. So variable selection, there's a whole field on how you select variables, and there's multiple different ways, and some are not good, I would say. So we'll talk about that, and others are better. In this class, we're trying to teach you how to come up with a variable selection technique that's clinically motivated. And that is really also in line with the other statistics classes taught at the University of Toronto. I know um, so I took statistics with Kevin Thorpe, and this is really mirroring Dr. Thorpe's methods of variable selection. I really think that that's kind of the correct way to do it. So I'll teach you about how to use a decision acyclic graph or DAG to frame your study before you conduct it, how to like classify your variables. And we really want to have our studies mirroring the clinical concept rather than using mathematical variable selection techniques that will artificially inflate our results. So I'll explain what I mean further. So classical model selection, uh, automated procedures, okay? And this is what I mean when I say clinical motivated versus mathematical methods. So in the classical approach, you can use univariate screening and stepwise selection. And this is kind of what we want to steer away from, I would say, and is usually the most used. And these methods are inherently flawed, resulting in lack of interpretability. So, does anyone know what stepwise selection is? Has anyone ever used stepwise selection in their research? It's pretty common. So, I feel like if someone's asked you to analyze something, they may have asked for this method before. So, stepwise selection is when you take all your covariates, test them for statistical significance, and then remove the least statistically significant variable from the list, run it again, and continue to remove the least statistically significant variable until all your variables are statistically significant. So, can anyone kind of think of what the issue is with that approach? If you're constantly just dropping the least statistically significant variable. Sorry? What kind of bias? Can you go further? That's correct, yes. Yeah, and selection bias, and there's stuff called collider bias. So basically saying that when you adjust for multiple covariates in a linear regression, there's interplay between those covariates that goes beyond simply the p-value. So when you start removing different covariates, there's relationships between those covariates that are also being affected that go beyond statistical significance. So if you are constantly just taking out the least statistically significant covariate, you may be um, yeah, you may be biasing your study and you're creating an artificial study compared to what's happening in the real world. So in the real world, you have all these variables working in concert with each other, like working together. Whereas in your model, you're just inflating the p-values because you're taking out those non-statistically significant variables. So you can also really inflate your p-values. So this is also they call this golden path bias. So you're you're ensuring that your study has statistical significance, that you have a positive result because you're taking out all those variables that have no statistical significance. Okay, so we tend to discourage this, and instead we want to use clinically motivated models as the replacement for this. Okay, so the problems with the classical approach: models should be generalizable to the population level. When you use stepwise selection, let me just zoom in a bit more actually. When you use stepwise selection, you're going to get excessive overfitting because, again, the population in which you fit the model, when you use stepwise selection, is going to be very tailored to that population at the expense of applicability to outside populations. Okay. Um, so generalizability, what kind of validity does that fall under? Does anyone remember from research methods? I'm sure you've covered this. So there's internal validity, right, which is bias, which we'll do today as well. And then there's, I remember, what's the opposite of internal? External, right? Yeah, external validity or generalizability. So that is, do your study results apply outside the sample? So that's also what we'll be talking about today, um, how to validate our results at a sample. So specific consequences, it will overestimate the R squared because if you constantly take out the least significant variable, it will just pump up that correlation estimate. You're going to get inaccurate distributions for the F and chi-squared test statistics. You're going to underestimate the standard error and overly narrow confidence intervals. You're going to get spurious p-values that are difficult to correct, inflated absolute values of the regression coefficient, and ineffectiveness at resolving collinearity. So that's interesting. So collinearity, recall, is when the variables are covariating together. What collinearity is going to increase because you're constantly taking out those variables that are not associated. So only highly collinear variables are resulting. And as you're pulling out those non-collinear variables, you're really inflating that collinearity because you're leaving only the most collinear left. So we can see here if you actually look at your assignment matrix when you had that one question where it asks when you increase sample size, what happens, decrease sample size. If you look here, can anyone kind of summarize what the consequences are doing? Like, what is it doing to our effect estimates? Is it making them more conservative or less conservative? Are we increasing the chance of finding a spurious result or decreasing the chance? So I'm not saying it correctly. Uh, so we always want we're always caring about bias. We're always worried about if bias is going to make our study detect an incorrect result. And if bias is against our study, that's okay. Because if you're biasing against your own study and it still shows statistically significant results, then you're really confident in your results. But what this will do is this will actually overstate your results when you use stepwise selection. So you're more likely to report and have that type one error. So that p you're more likely to reject the null hypothesis when you should have failed to reject the null hypothesis. Okay, not good. Recall that's the worst kind of error in medicine. Well, uh, considered the worst kind. So that's when you conclude that something works when it doesn't. Okay. Conclude there was an effect when there isn't. So you're really increasing the likelihood of doing that by using the classical approach. There's any questions so far about stepwise selection before we move on to conceptual models and conceptual frameworks? Okay, great. Um, Julia, are you able to load your RMS and HMISC package? Okay, because when I tried, it was giving me errors. So just
Which was it? H.
both of them were giving me Fortran errors. So HMISC and RMS. So just a heads up. Okay. So avoiding the pitfalls, what can you do instead of stepwise selection? We can use conceptual models. And I encourage you, well, you'll be doing this for this class, and I'm sure you'll be doing this for methods as well. And you will be doing this for your capstone assignment. I know it seems far away, but it will creep up faster than you think. And the conceptual model is the first step. Okay. So you want the selection of variables to be theory driven or literature review driven, represented using a directed acyclic graph, also called decision acyclic graph. And the guidelines, so you want at least 10 to 20 observations per coefficient is recommended for linear regression models. Does anyone know why the 10 to 20 is kind of the minimum? I'll give you a hint. We talked about it in past lectures. What's that magic number that we start to get that statistical property after 10, 20? Anyone remember? Starts with a C. Central limit theorem. Yeah, it is over 30, but you kind of start to get it at like we're talking like when you start to get into studies, you're going to see investigators wanting to do stuff with like 4 observations, 10 observations. So like the minimum is maybe 10. Okay. That you start to see central limit theorem. But 30 is like 30 on the T table is when it's 30 to infinity. After 30, you have central limit theorem, and 10 to 20 is dicey. But this is the absolute minimum 10 to 20 per observation. If too many variables are included, dimensionality reduction techniques that do not depend on the outcome can be employed. So I haven't put anything on dimensionality reduction, but again, we're kind of covering the material faster, so I may add that to the end of the course, just a couple of different ways. But minimum 10 to 20 observation per coefficient. You want at least 30. Does anyone know how many observations per coefficient? Like that's a continuous covariate. So when you have a categorical covariate, let me just add this. So when you have a categorical covariate, it's 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 observations per level. So for example, if there's 2 levels, you need 10 to 20 per level. So you need 20 to 40 instead of 10 to 20 because categorical is splitting it in half. Continuous is it's exactly the degrees of freedom on a continuous variable is 1. But as you increase the number of categories, you have to increase the number of patients. So we can quickly see, for example, if you had 100 patients and let's say 500 categories. So you said like, I don't know what uh, day of transaction, for example. Like, so you had 500 days of transactions, one per patient, and you had each categorical variable as one day. Quickly, you would see for 100 patients and 500 categories, there's many more categories than patients, so your model's not gonna work. You need when you have more categories, you need more observations per category. So this is why um, if you've ever done a study where there's 10 or 20 categorical covariates, this is really common. There's just, multiple categorical covariates. Remember that each of those categories has to be powered. So your categorical covariates really chew up sample size faster than anything else. That's why it's always recommended to use continuous covariates, especially with small sample size. So okay, okay. Let me just save or forget. So save variable selection. What we want to do is instead of eliminating variables with the lowest p values, we want to eliminate variables with negligible variability. Does anyone know what that means? I've kind of spoke about this here and there before, but the variance is close to my heart. Yeah, but oh, just stretching. Okay. Okay. Um, so why might we want to do that? Remove variables with negligible variability. So let's say I'm trying to predict success in school and everyone has an A in this class. How, what would happen to my predictions if everyone has the same value? Anyone? Yes. I'll just repeat for the recording. So if there's no variability, if everyone has the same value or a substantive portion of the population has the same value, there's no variance, therefore there's no prediction. So if everyone, let's say, if I'm trying to predict, I don't know what, average height, and I have a categorical variable saying above 4 feet tall and below 4 feet tall, and everybody's above 4 feet tall, there'll be no prediction. Everyone is the same value. Okay. So does anyone know what usually the cutoff is for variability? There is actually like a kind of uh, cutoff value for variability. Does anyone know? So usually we want about 10% variability for a variable to include it to be included in a regular model. Now, uh, so I'll say the usual threshold. Now, that doesn't mean if something's at 8 or 9% or 7%, it doesn't mean you should take it out automatically. Anything approaching zero technically can predict. In hyper rare outcomes, so for example, I did a project on childhood cardiomyopathy. There's only 12 deaths a year from this disease out of all the children in North America. There's only 12. So it's like 0.0000. It's to the fourth decimal place death percentage. And so, for example, for that, the variability is extremely, exceedingly low. But so in this class, I'm talking on the generality because we're usually dealing with people trying to get pregnant and people with malignancy or other pathologies. So those are usually we're not seeing to the nth decimal place. You're going to see some variance. So the usual threshold is 10%, but um, variable selection is more complicated with extremely rare events. And can anyone think the corollary, so the opposite. If it's complicated with extremely rare events, it's also more complicated with extremely common events if everyone has something. So, for example, COVID-19 is really tough because probably everyone's had it by now, so it's hard to do comparisons, right? That's a decent example. You're not going to find COVID naive. Well, it'll be very difficult to find COVID naive patients at this point to study. So, or extremely common events. The other one that crosses my mind is asthma. A lot of people have asthma. Over 50%, I think, in the province at one point or another will have asthma, and diabetes too. Diabetes is 33% ish, depending on how you measure. So these are diseases now that are so common that they're more like once it goes past 50%, once it becomes more common than not, then it's that's just an interesting thing. So you want variability, you don't want too much, and you don't want close to zero. Okay. Uh, Variables with excessive missing data may be removed based on the modeling objective. Does anyone know what the missing data thresholds are usually that we think about in research? And I think we're going to do some imputation now in this class too, in the last class of some missing data approaches. It's nice and automated in R now. So anyone know the thresholds for missing data? I'll give you a hint. It's similar to the variability threshold. So there's no defined rule in research on this, but there's some kind of general rules of thumb. So if you're below 5% missing data, that's usually the threshold for which you don't have to perform any additional. You can simply, if it's under 5%, you can probably just do like drop the observation and not have to do any additional statistical modeling. So 5%. Yeah, less than 5%. Let me just zoom in a bit more for you. Now, 5 to 10%, you should consider doing some sort of missing data imputation. Does anyone know what kind of things we can do for missing data? Yes. Yeah, yeah, that's a good one. Random, yeah, sure. Depends. So you have to think of, I'll get into this more. I think we should do some missing data, actually, it'd be fun. So you could randomly assign a value based on the distribution of the variable that is missing, for example. So not completely random. Like you wouldn't, for example, like on a blood pressure measure, you wouldn't take like a million or something. You would want it between the plausible values. And usually not random. We assign based on the distribution. So for example, you can assign based on the distribution of one variable what it's more likely to be, for example. Like you wouldn't want to, it would be unlikely for the missing value to be some sort of highly uh, extreme value, right? You would want to impute a similar value. So I'm kind of telling you the answer. What's another way to impute? Mean imputation, right? So you can look at the mean of the present variables and impute the mean. The other way we could drop the variable completely. So we could just drop the observation. And we could use has anyone ever heard of last observation carried forward? No? No trial. Does anyone doing clinical trials in here? No, no trialists. Okay. So last observation carried forward. Can you guess? It's in the name. Uh, in a longitudinal study, if you have a missing variable and there is a past observation with that variable, you simply assume that the variable hasn't changed. And it is pretty rational in a lot of cases that that is the case. For example, um, So in cancer staging, for example, if a patient, the stage is not recorded and you don't have it, and in the absence of the other covariates, you could say, oh, if they were stage, I guess, two, and there's an observation in 6 months, you can assume stage two again, theoretically. For example, that's one example. So last observation carried forward. Now, there's also something called last observation carried backwards. Can anyone guess what that is? So suppose you don't have any, like you suppose the missing observation is the first observation or a middle observation where the last observation doesn't make sense to carry forward. It makes more sense to carry the uh, next complete observation backwards. So that's the other way. Some studies, it actually doesn't matter. I've done studies where we do last observation carried forward because that makes sense. And then if there's still like first observation missing, we can do last observation carried backwards as well. So that's just another method. And then the more complicated, so mice, so that's multiple imputation. So this fills in missing covariates based on the distribution of the data set. So I'll say that. So for example, if you have a patient, they're missing cancer stage, but you have uh, tumor size growth, and you have all these other data that suggest that their tumor is getting worse, you could reasonably infer based on the relationships in the data that the patient's stage would be whatever increased, right? So let's say like the tumor size grew, I don't know, uh, 50% or something. Yeah, 50%. And you see, or let's say in another data source, you see that it has migrated to satellite sites. Like if that's like a categorical covariate, we know if it's migrated to a satellite site, it will increase the staging from a cancer that's contained to one single site. Like that's an auto stage increase. So even if the data is missing, that's called logical imputation in that case. But multiple imputation looks at the distribution of all the covariates in the data set and says, based on the relationship of the present data, what would likely the missing data be? So based on the present values, what is the likely missing? And then, yeah, I'll end with logical imputation, which is rule-based. So for example, uh, let's say you're missing if the patient is alive or dead, but they had the observation, you could logically infer that they're alive, for example, right? Uh, or if, so these are kind of errors that occur, but you can logic them out, okay? Uh, and I'll just say the missing cascade is the last one I'll talk about. So missing cascade is when the missing data of each individual covariate is low. However, so let's say you have a 10 patient data set, or no, let's say 100 patients, 10 variables, and they're 1% missing per variable, let's say. Sounds pretty good. Low missing data. However, if that 1% missing data is distributed across the patient, so if it's 1% per variable, but each unique patient has a little bit of missing, it could be that it could be up to 10% or even higher. It could be 10% plus patients with missing data, meaning if you dropped patients based on complete cases, you will lose massive sample. So this is also called the tyranny of small decisions, or the death by 1,000 paper cuts. So you can have minuscule amounts of missing data per variable, and then have it actually add to a problem. So that's why it kind of matters. You may want to just employ these methods to avoid that complete case problem. Okay, so a bit of a tangent on missing data, but we'll hopefully use that later. Any questions about missing data, data completeness? No. Okay. So now in the case where multiple variables are interrelated, so can you think of an example? I can think of an example. So, for example, I was doing a project where they had the weight in kg of the patients, and they also had the z-score weight, and they want to use both together, but they're the same thing. It's the z-score of the weight and the weight. You're going to get it's going to be extremely collinear, not good. Or BMI. Again, if you include BMI and weight in the same thing, it's correlated because they're together, right? So in cases where multiple variables are interrelated, offer the most clinically relevant or reliably measured variables or amalgamate them. Oh, that would, or make a composite variable. Amalgamate is not. And cluster analysis can be useful in this context. So we can cluster the patients by category. Okay. Okay. So so this is a directed acyclic graph. Let me orient you to why it's named as such and what it is. Let me just come in a bit. Oh, hold on. That was the max zoom I had to. Well, let's switch to here. That's better. Okay. So a couple of things. The first word, directed. So it has to have a direction. It sounds silly, but um, key thing. Acyclic meaning it can only proceed in one direction. So it can only go from exposure to outcome. It can't be reversely going. Now, if you see here, it says acyclic, but we see something going backwards. The confounder is a unique variable that is related inversely to the exposure and the outcome. So that's the only one that can kind of go backwards, but it proceeds in one direction. So can anyone think of something that always ensures that we're proceeding in directionally one way only? Like what X variable makes sure that we're only going one way? Time. I heard someone say it. So excellent, excellent. Time. So if time is on your X axis, it's always going to be acyclic because no matter what technology, we can't go back in time. Uh, so almost anything else can so a lot of stuff can be cyclical, but we have to come up with a study concept that's acyclic. So you have to think exposure outcome, and they have to be in that order. So the first thing is defining your exposure. The second thing is your outcome. Note the arrow. Okay. Effect modifier. So that's effect modifier is where you hypothesize that there'll be a distinct relationship at each level of the effect modifier. That will always be a categorical covariate or multiple categories. Okay. So the modifier is like there's a relationship at one level and then there's a separate one at the other level. So for example, I'll say men and women in rheumatoid arthritis. For some reason, men typically have worse disease, same disease, but there's some sort of gender difference uh, in the biology where it attacks the joints worse in men, and at the same age, men typically have more severe disease compared to women. That's one example of an effect modifier. That's usually the one that gets tested, actually. Um, now, let's look at confounders and predictors of the outcome. So confounder is unique compared to all the other things because confounder is related to your outcome. So you see the arrow to the outcome, but it's bidirectionally related to the exposure. Okay. So um, this is what a confounder is. So it can make it look like our so what's one that I like to use? So for example, if we're looking at the effect of socioeconomic status on lung cancer, for example, and we think of smoking as a confounder, right? So socioeconomic status is the exposure that could cause you to be more likely to smoke, and smoking may also affect your socioeconomic status, for example. And then smoking obviously is going to be related to the outcome of lung cancer, right? But I guess in this case, plausibly, lung cancer, can't make you smoke. So that's the trick here. So you see this arrow is bidirectional and this arrow is unidirectional. So that's how you can kind of in your head conceive, is it a confounder or is it a mediator or predictor or something else like that? That's what you have to think about. So mediator is only related in one direction. It's not see the arrow is only one way, right? Now predictor is a bit different. Predictor is simply a predictor of the outcome. Again, it doesn't relate back to the exposure. So you have to really, a lot of people ask me, oh, like, how do I know which one's which? You have to read, this is literature review, this is thinking, and you have to get expert opinion on this, and you have to read and think of what's biologically plausible. Okay. And it's not always, people have differences of opinion as well. What's a confounder? What's a mediator? A lot of the time, statistically, they get treated the same. But for your statistical models, you need to make sure that you have this filled out, and you should have in your assignments, you should have these titles and the variables listed. Okay. And the units. Important. All right. Any questions about decision acyclic graphs? Okay, good. Okay, so I'll speak a bit about effect modifiers, effect modification, and interaction terms as well. I don't think we've covered that yet. So effect modification, also known as interaction, a fundamental concept in epidemiology and biostatistics. It modifies the primary effect of an exposure on an outcome variable by a third variable. In the context of linear models, the concept of effect modification describes situations between the primary predictor and the outcome that vary across different levels of another variable, termed effect modifier or interaction term. The presence of this effect modifier implies that the relationship between the predictor and outcome is not constant, but depends on the level of another variable. So when you make an interaction term, it's almost like saying you're making separate models. So if you have an interaction term like a binary, like yes, no, there'll be one model for yes and one for no. If it's split by four, like if you have a Likert scale, poor, what is it? Poor, good, excellent, let's say, like a Likert scale of three, there'll be three separate models. So recall what I said before about number of observation needed for your study. Interaction terms quickly use up sample size, okay? Because they split the model basically. So you're going to use a lot of sample size with interaction terms, and I'll show you how to calculate that in a second. Okay. So consider a simple linear regression model where y is the outcome and x is the primary predictor. Let me just try and zoom a bit more. Yeah. Yeah. So recall, it's y equals mx plus b again. So our y is our outcome variable. Our b0 is our y-intercept. b1 is our predictor, our first predictor variable. b1x is the beta coefficient of 1. And e, does anyone remember what the e term is? Random error, right? Study error. We don't, e is like a theoretical constant. We don't have a metric of e. It's just, it's your beta coefficients plus whatever random error you have, okay? So when a variable Z acts as an effect modifier. The linear regression model can be expanded. So we have y equals beta 0 plus beta 1 times x plus beta 2 times z plus beta 3 x times z. Okay. So when you have an interaction term, you not only include that variable as a linear predictor, but you also include it as an interaction term. So what you have to remember is every interaction term includes those interior terms as a linear predictor as well as an interaction predictor. That's usually a tough one for people to grasp. So let's say, yeah, let's say you included biological sex in your study and you put it as an interaction term, you would not have to put that as a linear term as well. It will be included as a beta coefficient and as an interaction term. Okay. So just to let you know. So here the beta 3 is the coefficient term for the interaction of x and z, and it quantifies the effect modification. Statistically significant beta 3 implies the effect of x on y varies depending on the level of z. And I'll show you how to test effect modifiers and not having them. So the types of effect modification, there can be qualitative interaction. So the direction of the effect of the primary predictor of x on y changes depending on the level of z. So for example, x could have a positive effect on y at low levels of z, but negative at high levels. You could have quantitative interaction. So the magnitude changes at different levels, but the direction remains the same. So like I said, I'll show you pictographically. So how do you test an interaction term using statistical testing? It's a little bit different. The statistical significance of an interaction term, or beta 3, is tested using hypothesis tests like the F test or the T test within the linear model framework. A statistically significant interaction term suggests the presence of an effect modification, warranting its inclusion as a stratified model. So, ah, and effect modification is not a statistical anomaly. You can use effect modification to lead to personal treatment plans, interventions, and target specific subgroups in a population. So, for example, one thing I can think of in cancer is there's certain genotypes for which certain treatments are extremely effective, and somewhere it isn't. So I know um, there's one subtype of colorectal cancer that I think they had a 12 patient trial and all 12 of them were cured after, but they had one specific genotype. So for one genotype, if you happen to have that, there's a really effective treatment. And if you don't have that genotype, that treatment is not at that effectiveness level. So that's a good example of a strong interaction term based on that genotypic expression. Okay, for example. Okay. Yeah, crucial to understand this. But we can also improve our predictive accuracy and to individualize recommendations, we can use it. Okay, so I'm going to revert back to my MT cars data set because it's inbuilt and it's just I think it illustrates it pretty nicely. Let's go back to our R session. Okay, and we're going to load our library ggplots2. We're going to see the data MT cars. And we're going to fit a linear model called fit1 without an interaction term. So recall the y variable, miles per gallon, right? And then tilde. And we have two predictor variables here. We have horsepower and cylinders, data, again, MT cars. So let's run that. and we'll get our summary command. Okay, so let's just interpret the beta estimates together. First, our intercept. Do we care about the intercept? No, does not mean it will help you maybe plot your regression line, but that even that not helpful. So we ignore that. Um, I had a student 2 weeks ago presenting the intercept term, so it does happen. Um, so horsepower, the estimate negative, and cylinders, the estimate negative. So can anyone give me the conclusion here for each? Oh, nice. For each 1 unit increase in horsepower, what happens to miles per gallon?
Decreases by that number.
By that number.
0.01. Yeah.
Exactly. And it's not done yet.
Oh, and in terms of horsepower, it's not very,
Mm,
but with cylinder or sorry.
Adjusted. That's a magic word. Adjusted for.
Oh,
So a 1 unit increase in horsepower is a negative 0.01. You would say negative 0.01 increase in miles per gallon. Actually, you're supposed to phrase everything in the same direction. So you can say a negative increase rather than a decrease, but like that's the thing. If you have increases and decreases in the same thing, it's usually better to say a negative, like you always want to phrase everything in the same direction. Okay. So I would say a negative 0.019 increase in miles per gallon adjusted for number of cylinders. So you have to, in a multivariate regression, you have to include the word adjusted for. And if there's a reasonable number of covariates, like one or two or three, you can say adjusted for and then say it. If there's more than three or four, you can say adjusted for all other covariates listed in your. So you have to say adjusted for the other covariates. That's the key in multivariate linear regression. Okay, so don't forget. Yeah, but that was really good. Okay, and then you want to try for cylinders? Yeah.
and then for cylinders with every 1 unit increase of cylinders, the miles per gallon decreases by two, increases by negative 2.265.
Right.
Yeah.
Exactly. Adjusted for.
And it's just adjusted.
Yeah. Oh, that's a really good question. This is in original units. So, okay, so car talk, but the number of cylinders is going to have a larger increase in sorry, a larger decrease in the miles per gallon because as like a cylinder is like a big difference. Like the engine is going to increase significantly in size, whereas horsepower, like 1 horsepower, not a big difference. Like it's a marginal increase in power. But a cylinder is like the difference between a 3 cylinder and a 4 cylinder, or like a five and a six. It's a big difference, right? So that like the effect sizing that you're seeing here actually does make sense in relation to the yes, in relation. So it's 1 unit in the original units, yes. Here. Yeah. That's a really good question. Of course. Yeah, that's a good question. So you have to look at the format of your variables. So two-way ANOVA. So do you have a 2x2 category, for example? Like do you have like um stage one, stage two cancer and like bigger than like you get if it's two categorical variables and you're doing 2x2, you're going to do ANOVA. But if you have a continuous outcome and um one linear predictor, you're going to probably use a linear model. You have to look at your exposure and your outcome and your covariates. So again, like let's say ANOVA, right? How you can't adjust for confounders with ANOVA. because ANOVA is just testing are the two groups different. It doesn't say are the two groups different accounting for so for example, yeah, we'll use our socioeconomic status and lung cancer example. You could do socioeconomic status, high, low, lung cancer, yes, no. That's two by two. You can ANOVA test that. But now if I say to myself, oh, I want to adjust for smoking, cannot do that with ANOVA. You'll need a regression term. So it goes back. That's a really good question, actually. So when we go back, it goes back to here. So it depends on it depends on what you want. So for you, if you're doing biosamples and you just want to see are the means of three or more groups different, you just want to see raw difference in means unadjusted for anything else. And that's not saying that that's wrong. You start there with ANOVA, right? So you're testing the difference in means between groups. Is at least one different, or are they all the same? And then you may say, okay, we know there's at least one difference. Now let's plug in a hypothesized exposure and outcome and our covariates. You may have the biological samples, but now you may want to see biological samples and then a confounder of age, confounder of gender, SES, whatever else you have. So it's more robust, and it can let us adjust for these other things. Again, and effect modifiers, predictors. So yeah. So it tells you different things. The beta coefficients tell you the relative contribution of this variable adjusted for the other variables. If so, let's say you excluded cylinders, for example, and you just had horsepower. Um, there can be different there can be different relationship there. It tells you something different. Okay, so okay, summary fit one. All right. Now we're going to fit a linear model with an interaction term. So remember I said before that when you have an interaction term, it also includes both as a linear term. So this model subsumes this model as well. So it will be this plus the interaction term. So let me show you. Now to do an interaction are really easy. Instead of doing plus, you just do an asterisk, which is multiply, and that's what you're doing. If you go back to the equation, oh, excuse me, it's multiply, right? So it's nice that when you go into the R, it follows the same notation. So it's internally, I would say, congruous. Okay, so let's run it and see what happens. Okay, so really interesting. So we see two beta coefficients, one for horsepower, one for cylinder. So those are the original linear predictors. So remember an interaction term, you're going to get both as a linear predictor. Now you see a third thing, you see horsepower colon cylinder, right? So this is the interaction term. Do we have statistically significant? It is. So this is the estimate at the horsepower level. Actually, how many horsepower do we have here? Um, this is a bad one because there's so many different horsepower that it's going to give a non-informative answer. But it's saying, so it's with horsepower as the reference group, the interaction term is saying um, how it's going to change at each level. So let me just show you. Okay, hold on. Let me show you visually what I mean. It'll be easier. Oh, where'd it go? Okay, yeah. Let me just show you. Okay. Yes, here we are. Just zoom out a little bit. So this is a graph of that linear model. So we're saying the interaction between horsepower and cylinder on miles per gallon. So actually it did the interaction at each level of the cylinder. That's what we wanted, not at the horsepower. That makes more sense. There we go. So it's horsepower given cylinder. Okay. So we see here 4, 6, 8. So um, we see it's a different relationship depending on the number. So we see for the 4, as you add horsepower, it really, really, really decreases. And stratifying versus this. So the interaction is stratifying, right? So this is so how think about it this way. How would you go about stratifying? Yeah, that's what it is. An interaction term is stratifying. So it's saying there's remember I said there now it's like making a whole different model. So we have one for the 4 cylinders, one for the 6, and one for the 8. Um, so the difference here that now I'm seeing it, yeah. So the difference here is when you add the interaction term, okay, you see that the relationship when you add a cylinder goes much more negative. See that? Um, but only at the 4, right? So you're going to multiply. So when you do the beta coefficient, right? Let's say you had in this example, so you put your y-intercept, you have your beta 1, you have your x. So let's say you have a 4-cylinder car, right? So this is going to be 4. The beta 1 will be negative 4.4. The beta 2 will be whatever it is. The beta 2 will be the z variable, so it will be the interaction term. Now here, the beta 3 x times z, right? So it'll be your cylinder term times the interaction term. So that will actually give you like this likely relationship here. Okay. Uh, do I have another example? I do not. So this is an example where, like I said, the relationship changes at each level of the category. Usually, usually the one that is tested a lot is gender in clinical studies. You want to see is there a different relationship between men and women a lot of the time, or senior or not senior. That's another one that's common, like plus or minus over or under 65 is a common one, or other clinical cut points that you care about. Yes.
So is the beta coefficient that it gives you for the interaction term like a combination of all these?
Uh, So it's going to change. So if you look, it changes the linear relationship. And then when you plug this is like the weighting coefficient in the actual regression equation. Okay. But we see the we see that the interaction term itself has a statistically significant value. So that's telling you it does make a difference. It does modify the relationship that we're looking at. Okay. Okay, so predictive versus fitted values, really important. So you need to know about prediction and fitted values for model validation, interpretation, application. I'll show you how to do that. We talked about it a bit last week. So the fitted values are estimates of the dependent variable y obtained from the observed values of the independent variable x using the estimated regression equation. So remember, with regression, it's not only getting beta coefficients, but it's saying you can use it to predict. So these lines are like if I said to you, oh, I have a car with 50 horsepower and 4 cylinders, you go to the graph and pick the spot and tell me, oh, you're going to get 27.5 mpg probably, right? That's what regression is for in the end, is to be able to predict. So how to do that? We can use predictive values, which are estimates dependent on the variable for new on. So fitted values, existing values. So we use our regression equation to see the fitted values in our within our equation. Predictive values are using the estimates of the dependent variable on a new value to look at the unobserved or independent variable. They are also derived from the regression equation. When we see this little hat here, anytime we see hat, that means predictive. Okay, so y hat is y predicted. We get it from the beta 0 hat plus beta 1 hat x. Okay. Okay, I'll show you how to do that. We can use fitted values for model evaluation to assess the goodness of fit, to assess measures like r squared and the residual sum of squares calculated based on the fitted values. We can use it often for diagnostic plots. So we can use it for various diagnostic plots to check assumptions like linearity, homoscedasticity, and normality of residuals. So we've Julia covered that especially in a tutorial last week, but this is really highly useful for looking at your model diagnostics. So fitted values help in understanding how well the model explains the observed data and helps you visualize the relationship between X and Y. And also, if there's any deviance of hypothesized relationship along the curve of along the x-axis. Okay. You can use predictive values to forecast to make future projections, which is the primary objective in many practical applications like finance, engineering, or healthcare. You can use it for risk assessment, for example, in epidemiological studies. You can use it to assess the risk of an outcome occurring under specific conditions, so predicting risk. And you can use it for decision making. So you can inform strategic decisions in business and policy by providing a quantitative basis for various scenarios. So if you can say the expected predicted outcome of a decision is whatever it is, you can kind of determine your appetite for those different decisions. Okay, so let's get back to R and see some R code. Okay, we're gonna use cars again, and we're gonna use univariate linear model. So this is just horsepower and miles per gallon. Okay, uh, we're gonna just check. So again, a negative beta coefficient. Now, to calculate the fitted values, we use and we've assigned the model name to be called fit model. Okay. To calculate the fitted values, again, we're making a variable called fitted values. We're using the function called fitted uh, for the fit model. Okay. And let's just take a look. So this is for each car, the predicted MPG based on the horsepower. Like this is a predicted MPG for each of these cars. Okay. I don't know what these are, but it doesn't matter. It's showing you. So let's try and make a new data frame for prediction. So let's say we have a new data frame. Okay. Uh, we have a data frame with a car with a horsepower of 100, 150, and 200, for example. Okay. Now we're going to predict the values. So we use the function predict. We use this is the argument. So this is the model that we need to predict from. So we tell it what model we want to use, and we set the new data value. So for example, this is the model that you've derived your predictive model from, and then this is the new data set for which you want to make the predictions for. Okay. Let me see. And here are our predicted values. So based on our model, for a car with 100 horsepower, we predict 23.27603 miles per gallon, 150, 19.86, 200, 16.45. And it's interesting when you look at this, because if you go from 100 to 200, you don't see it doesn't double here. So just to just give you an idea, it doesn't have the fuel economy. So you can just see visually that it's taking from that actual regression model. It's giving the predictions based on a regression model. So this is extremely simple to demonstrate the concept, but you can hopefully see the extensibility to more complicated data sets, to your data sets, and so forth. Okay. Let's do a scatter plot. So again, back to our handy ggplots data, X empty cars, which is the data set, AES, which is giving the axis. Okay. So the X-axis horsepower, Y-axis miles per gallon. These geom point variables are going to give these are visual options to make the graph look nice, but they don't serve a mathematical purpose, just for visual. And then here, so this is more important. So geom smooth method LM SE equals false AES is regression line. So this is the actual regression line plotted. And again, we're going to end with our labs, which is our access titles. Really important, but just to tell you what each thing is. Okay. And let's go back to HTML. So we see here actual values in red. So that's our original data set. Okay. Our regression line is the blue line, and our fitted values. So those are predictions based on our given data. So what can we see here? What do you notice about the fitted values compared to the actual? Maybe I'll zoom in a bit. It's hard to see. Yeah. Anyone? So the actuals have variance in the Y, whereas the fitted are just always on our have no variance in the Y. So that's great. That's great. So we notice here there is variance in the actual data, but in the fitted, they're right on the regression line. And that makes sense because the regression line is the average. Remember, it's the lowest uh, mean squared error between the data points, right? So why would you add in error into your fitted values? It doesn't make sense. You're going to predict right on that line for each. So for each X value of horsepower, which we've been given, you're going to predict right along that regression line. Okay. It makes sense. Just to visually show you what the difference is. Okay, let me yes, okay. Is that clear for everyone what the difference is? So again, red points, the data for which we derive predictions. Blue line, the regression line, which minimizes the variance in the Y axis. And the green points is the predictions for a future data set. So given our X value, what is our predicted Y value? Okay. Okay, so comparing linear regression models using the partial F-test. So here's the fun part. How do you evaluate which models are better than others? And how do you do variable selection with some sort of math, but that's not stepwise selection? So you may need to evaluate whether a subset of variables significantly contributes to the explanation of an outcome. For example, you may have a basic set of variables that are known to be predictive, and you want to see if an additional set of variables would be significant. So should you add to your model? Or the other thing that this can be used for is, I said before, supposing you have two variables that are very similar, you may want to pick which one to put in. That's another way that you can use it for. Okay. So you can use the partial F-test, commonly used to test whether the additional set of variables in the model significantly improves the fit compared to a reduced model. So here's the equation. So the sum of squares RF minus the sum of squares R over P divided by M, the mean squared error of the F. Okay. And I'll show you what each of the terms mean. So the sum of squares RF is the sum of squares due to the regression for the full model. The sum of squares RR is the sum of squares due to the regression for the reduced model. So the little subscript is F is full, the little R is reduced. Okay. And then the mean squared error for the full model. The p-value is a difference in the number of parameters between the full and reduced models. So if you're testing a variable with 10 covariates versus 9, the p will be 1, for example. Okay. Okay, the requirements to use a partial F-test, both models must be fit on the same set of observations. All variables in the reduced model must also be present in the full model. Clear so far? Okay. So let me show you how to perform a partial F-test using the ANOVA function. So again, not to belabor the point, but we'll just keep using the cars data set for continuity's sake. So we load in the cars data set. We're going to fit two models, the full model and a reduced model. One model with miles per gallon as the outcome, horsepower, weight. Now, Q sec is number of seconds for the quarter mile, I believe, or some sort of acceleration number. So less seconds means a faster car, and more seconds means a slower car. So theoretically, if the car is faster, it should be burning more gas. So just to give you the background, and then the reduced model without that qsec variable. Okay. Now note these are all continuous covariates and a continuous outcome. Okay. So our degrees of freedom. Remember, cars is a very short data set. It's only 32 obs long, so we don't have a ton of degrees of freedom. But with three continuous obs, we should be okay. All right. So let's fit these two models. We perform the partial F-test simply by using the ANOVA of both these models. Ooh. So again, we see each of the values. This is the ANOVA variance table. It's always good to reconfirm your models, what's in them, just in case, because again, like this is a double check to make sure you're doing the right thing and that the variables that you think are in the model are in it. So you should always read the output, even if don't just skip to the p-value, like read the whole output because you can save some critical errors this way. So does anyone want to take a guess at the conclusion here for our reduced and our, so you can see here, our reduced and our full model and the p-value? What can we conclude about the addition of qsec to this model? So what does our ANOVA test? Go on. Take one step back though. What is ANOVA testing in the first place? Even less detail, like this is just high level. ANOVA tests if one or more groups from the other, right? So that before we get into the right, so is the p value here greater than 0.05 or less than 0.05? Greater, right? So are the groups different from each other? No. So the groups are not different from each other. So the addition of that q-sec variable, you could say, if they're not different, so the addition of that q-sec variable does not is not statistically significantly changing the relationship. For example, that's what you could say here when you look at this. I know it's complex remembering what direction everything is in because some tests are testing is there a difference and some are not, but so one model compared to the other, no statistically significant difference between the two. Okay, and a partial F test. Okay, all right. So it's a leave one out methodology here. Okay. Now this is different from stepwise. Stepwise is test every single thing at once, leave out the significant, test every single thing again. We're not doing that here. We're just saying leave one out. So you could test every single variable like this as well if you wanted, but yeah. Okay, let's go back to HTML. Okay, so influential observations in linear regression. You may have outliers or influential observations that could significantly impact the characteristics of a fitted linear model, including both the estimated coefficients and the fitted values. We want to estimate or understand the influence of these observations, which is critical for the robustness and interpretability of the models. So here are some ways to do so. You can use DF fits, which for an observation is the difference between the fitted value, the y hat from the full model, and the fitted value for that same model calculated from a model that excludes the observations. DF fits is normalized by the standard error at that point. So for example, normalized by the standard error, meaning if there's huge amounts of variance and you have a data point with a large amount of variance, probably not impactful. But if there's very little variance and you have a massive outlier, more impactful. And again, this uses the leave one out methodology as well. So it's saying if we have a fitted value and exclude it versus include it, what is the difference? DF betas measure the influence of an observation on the estimated coefficients, also normalized by the standard error. For each observation, there's a DF beta for each coefficient in the model. So DF betas, you can literally get a list of every single observation, every patient with an observation that has an influential value. So DF betas will return a patient list and a list of outlier values for you in your R output. Okay, and the hat values. So hat values, a measure of the leverage and indicate an observation's influence on the regression line. And my formatting has been chopped up a little bit, but we go back to R for an example. Should be like that. So again, back to MT-cars, how to calculate influential measures using the MT-cars data set. Let's do it. So we're going to fit a linear model. Again, a Y outcome of miles per gallon, X variables of horsepower, weight, and I think it's seconds of the quarter mile. So we'll run that. Now to calculate the DF fits, we're going to use the function influence.measures. We're going to specify our model. Now, this is simply, so we've spoken a bit about this in tutorial, but it's worth mentioning here. So let me show you without this additional notation. Let me just show you, I'll call it test. So when you run just the influence of measures fit model, and then you just save that, this is the output. So think of this like a patient ID. We don't have patients here. We have motor vehicles. So this is like the ID variable. And we have the DF beta dot one, the DF beta for horsepower, for weight, for QSEC, the fits, the covariance, the Cook's D, and the hat. So we have a whole bunch of different influential observation metrics. What this R code lets us do here, this dollar inf mat uh, comma hat, what it lets us do is it lets us pick just that hat column, I believe. So let's just yeah, that for this one is the hat column. So dollar inf mat. So if we go, we say oop, where's my oh here we go. Oh my test got deleted. It's all right. So we'll try again, just like that. So the difference is when you when you run this, it's making so this package makes an object called test, but the object contains several sub objects. So for example, the information here, when I say test, it's stored here. We see this little like it looks like confetti here, but that's telling us it's an object with its own parameters. So if we click test dollar, there's three sub tables available. So we can go is inf call or inf mat. So if we go test dollar inf mat, it gives us this table here. So what this function is simply telling it to do is it's saying, give us from the table inf mat. It wants the column df fit to give us our fit df fits. So you could just use influence measures fit model and just manually do it. But I'm asking you just for the df fit, this is how you just select that column. So a bit of R data formatting for you. And if we ran that fit underscore df fits, it should show us just that column itself. Yeah. So it just shows the patient and the df fits. It doesn't actually show the other values. And then the same thing here. So df fits, calculate the df betas. So there's a df betas function for the fit model. And then the fit hat, again, same thing. Influence dot measures, dollar inf mat, and then select hat instead of df fit. So let me just show you the results here. So this is the yeah, this is the hat values. So this is how you would pull the influential observations, for example. So let me show you some scatter plots now. So how to calculate and also visualize the influential observations. We load our ggplots data. We set our linear model. We calculate the DF betas, the DF fits, the hat values, and now we're going to plot them. So, and a data frame. Yeah, let's take a look. Go back to here. Let me zoom out a little bit. Okay, so our scatter plot of our DF fits. So if there's no influential observations, they'll be clustered right at zero. So zero is like null. Okay. Above and below zero are both influential observations. Okay. Now it's a the I don't like the scale of this. It should be like equidistant scale. It kind of is a bit misleading. It should show to the same like -1 here. The values are by magnitude, not by the actual number. So -1 is equally as influential as a +1, for example, here. And same thing, like -0.5, +0.5. It doesn't matter the direction, it matters how far this is away from the y. So you can see each of these observations. Uh, Again, most influential observation, for example, here, right? Now a box plot for the DF betas. This is DF fits, box plot for the DF betas. Again, zero being the null. And this tells us the box plot, again, remember the characteristics of the box plot. It tells us about the skew of the data. So this not only shows us the influential observations, it shows us if it's really skewed in one direction or the other. What do we think here? Is the data, the DF beta is evenly distributed? What does it look like? So what are we looking for? We're looking for Q1, Q2, right? Median, Q3. So this. Are those even? Pretty even, right? The only thing you see one, again, the scales are slightly misleading because there's an extra like half point out here, whereas there isn't out here. So try and think like this and this are equal. So there's maybe two extra points passed on this side. So it's these two maybe you can consider as influential, these two out here. Okay. But no, I wouldn't say a problem based on this box plot because it's almost completely even below and above zero. And then a scatter plot of the hat values. Now again, it's zero should be labeled here, but so the zero line is right across. Oh no, here it is. Yeah, the hat values. So again, the predicted hat values, not a ton of like outlier predictions. You maybe have two outlier predictions. So I think it's predicting pretty good. You don't have a ton of outliers. Okay, with that, why don't we take 5 minutes, be back at 10:40, and we'll be back and continue the recording. Let me just make sure I'm screen sharing. Yeah. Okay. So welcome back. We've talked about influential observations. Now let's talk about nonlinearity. And this is always a fun topic. What happens when the relationship between a predictor variable and a response variable cannot be adequately modeled using a linear function? In statistical terms, a model is said to exhibit nonlinearity if the model's residuals are not randomly distributed, or if a linear model fails to capture the underlying pattern in the data. So key phraseology here. Residuals are not randomly distributed, or that fails to capture the underlying pattern in the data. So it can be almost anything if it doesn't capture the pattern in the data. So a lot of stuff doesn't fit a linear line. Okay. So the types of nonlinearity, among others, nonlinear relationships can manifest in different forms. We can have polynomials where the relationship can be modeled using a polynomial function. So we see the difference here. B1x, linear predictor term, right? B2x to the power of 2, right? Polynomial predictor term. Okay, see that? Exponential, we can model using exponential function. So it takes the relationship beta 0 multiplied by the exponent beta 1x. Or logarithmic, you can use the logarithmic function. In this class, and usually we're going to use the polynomial function for nonlinear relationships, and it's definitely fittable in R. You don't have to do any you don't have to do too much custom coding. It's pretty out of the box available, which is nice. So how do you detect nonlinear relationships? You can plot the residuals against the predicted values or individual predictors to help identify nonlinearity. You can use statistical tests like the Brayish-Pagan test can be used to detect nonlinear patterns. You can use remedial measures like transformation, which I'm not a fan of, but some people do it. I don't. Or you can use nonlinear regression models, using a nonlinear regression model that better fits the data. Okay. So let's use our GG plus library. We're going to set our seed at 1, 2, 3. We're going to say 100 values. So again, let me just show you the generation. So sequence from 1 to 10, the length out is n. So it's saying um, repeat from 1 to 10 n times, so 100 times. It's going to give you 1 through 10. Okay. The y value is 3 plus 2 times sine x plus r norm n 0, 0.5. So that's telling you basically it's giving you a random y outcome variable for each of these outcomes of x. Now, not random, sorry. It's multiplied by the sine of x. So it's going to give you a sine wave distribution. So it's forcing a nonlinear distribution for this random data for this example. Okay. Then we're going to plot the data like usual. So again, here is our nonlinear relationship data on the x and on the y. So just a nicely simulated sine wave with some error. So they're not just right on. So we can see here visually, we don't need any testing here. You wouldn't fit a line of best fit to this, like a linear line of best fit, because it wouldn't make sense to do. I think the line of best fit here would probably be right down the middle, actually, like a horizontal line if you had to do it. Ah, did we do it? Oh, and then here is the yeah.
Why did you have to agree on the two?
Ah, um, it will. Why do I have the 3 and the 2? Um, it it gives us like the distribution of the variable. So we multiply the sine wave by 3 and 2, and this is like a random noise variance. So it's kind of going to give us like it gives us the values on the y-axis like in there. So it sets where on the y-axis is going to go. Okay. So fit the linear model, LM fit. Here we're going to plot the residuals. So we're going to get the residuals using resid, LM fit. We're going to plot the AES. So the X is the X, the Y is the residuals. We're going to tell it residuals plot. So the only difference here, it looks pretty similar, right? But the only difference here, if you see on the x-axis, the same, exactly the same. The y-axis is the residuals, right? So what do we know from the residuals? If there's 0, there's no variance. And again, from our residuals plot, we want to see across 0 through the whole distribution, or we want to see an equal amount of dots above and below 0, even if they're distributed far away. So like if they're all clustered here and all clustered here, that would be okay. But because we have correlation among the residuals, like we see a nonlinear pattern of the residuals, we know linearity assumptions have been violated now. So if the so again, like we see a pattern residual. So we couldn't use linear models for this, or if we were to use linear models, we would know that we have a spurious relationship. Okay, so we see 0, again, absolute value, -1, -2. And again, I don't like when they do this, when the axis is it should be completely equal just for you to see it. Because it goes to -3 here. So it's even worse actually, if you look at it, because this is like to -3 and none of these points rises to +3. So it's not only non-linear, but there's more residual balance on the negative side, like it has more extreme values on the negative side as well. Just to kind of orient you to what I would look at when I look at this. Okay. So see here, the most extreme is to -3, and the most extreme here is to negative 2.5, right? Okay. Okay. So uh, a nonlinear model, we can use the NLS variable, sorry, the NLS function, and we have our yeah. So we have our NLS function. We have our y tilde a plus b plus times sine c times x. Our start is start parameter. So this is again, this is our generated data, and our starting parameters are just one because this is like um how do I say it? This is our initial check to see if we can fit a nonlinear model. So here we have our estimate parameters, and when we plot, so we're going to plot, our method is going to be NLS. Our formula again is here, and our fitted nonlinear model. So again, our data here is fitting it much better. Now it's kind of cheating a little bit because I generated it using the sine function and we're inputting the formula as a sine function. So that's not really super realistic as to what is going to happen in real life. But I just wanted to show you kind of the difference in fitting a nonlinear term and a linear term. I think I have a better example coming up just with actual data and how you can fit it. So let's continue. Yeah. Okay, so here this is more applicable. So this is just an example, not really applicable in biological data. This next example you can use in your own research. So a new package here, we're going to load RMS package, and it's loading from RMS is loading HMIS, so HMISC. It's almost like there's R and then there's dplyr, which I mean Julia's been explaining a lot of that in a tutorial. And then there's another flavor, it's HMIS and RMS, so it has its own notation as well. Uh, now for nonlinear regression, the RMS package is a lot easier than any other way. So we usually teach vanilla R and dplyr in this class, and this is kind of the only RMS that we're using is for nonlinear regression. In Dr. Thorpe's biostatistics part 1 and 2, it's all RMS and HMS. So he's kind of leaned into that package, which is fine, but we use more general methods, and this is kind of the only RMS that we'll be using in this class, I would say. Okay. So again, we generate our nonlinear data like we have before, just the same nonlinear data set. We're going to create it as a data frame. So this is really important. So we make it as data frame X and Y. So we're actually loading it into a tabular format instead of just a concatenated list. Whereas here, this is just a variable N, X, Y, not analyzable. So we're coercing it into a uh, data set. Now, in RMS, there's this bit different notation. It uses data dist. So you have to assign your data frame as a data dist object. It's just a wrinkle. I don't think it's too big a deal. So you just say data dist data, and we're calling it object d dist. Okay. And here is a linear model with restricted cubic splines, making it a nonlinear model. So instead of LM, we're using OLS. Does anyone know what OLS stands for? ordinary least squares, fancy term for linear regression. You can call linear regression ordinary least squares, linear models, multivariate models. They're all kind of the synonyms. Same notation, very similar notation. Our y variable is y. And to fit a cubic spline, what we do is it's RCS. RCS stands for restricted cubic spline. The variable that we're fitting as a restricted cubic spline is the x variable, is our predictor variable. There's only one. And knots, four knots. So knots is um how many times the curve can change direction, basically. So the more knots you have, the more like kinks in the curve can happen. So if you only have two knots, you're gonna have like a parabola. If you have three, it'll be three. Uh, so I'll show you. It'll be more clear when I so actually it's a cubic spline. So okay, so here's your example here. So your plot of a restricted cubic spline for this data. So it's a cubic spline actually. So there's going to be two changes in direction. So one and two, right? So if you have a quartic spline, there's three changes in directions. If you have a quintic spline, there's four changes in direction and hex, sept, whatever. So it's always n minus one. So cubic is three, always minus one is two. So there's one, two changes in direction. See that? One, two. So you can change the number. Oh, I can't do it. There's a way to do it here. You can change it. I think do you remember how to do it? How to add additional
For what?
for the splines? How to make additional polynomials?
I think you just changed that, like the splines are like,
Isn't it here? Isn't it to the power of three or four, or whatever?
no, that's the knot, so like. That would be a knot, and then the bottom would be a knot, and then the top, like,
Ah,
one,
it is. It
two,
is. It is.
three,
Okay.
four.
Okay. Julia's got it. Yeah, that's correct. Yeah. So that is it for. So if you increase this number, you'll let the curve have more. Yeah, that's it. That's it. So the first point one, the second point two, third point three, the fourth point four. If you had five, there would be another like it would turn again, like it would continue like yeah.
So like the linear model, you use the two then for the one.
You wouldn't use a restricted cubic spline for a linear model. You just would eschew, like you wouldn't put that term. It would just be now. I wouldn't use RCS. You could use this function for a linear. You just simply would just put y tilde x plus, like it uses the same notation as LM. I just don't use it because I like LM. I like the graphic function better, but for cubic spline. So if I wanted a cubic spline and a linear term, I could also put plus uh, and then in my linear terms as well. So you can have cubic splines and linear predictors mixed together. Now, if you have a restricted cubic spline, you can it also includes the variables of linear predictor as well. So I don't need to put plus x. It's already implied here in the model. Okay, like interaction term. You don't if you have an interaction term, you don't need to put those terms as linear predictors. It's already implied in the model. Okay. All right. Okay, and then okay, so switching gears. Okay, so a bit switching gears. So not talking about regression now, talking back to accuracy of the test. So we spoke. Okay, are there any questions right now about nonlinear models? To get the actual values in the nonlinear model, you have to use those predict functions because it's nonlinear, so it'll matter where on the curve you are. You have to use those fitted values to get those predicted values of your next patient. Okay. Okay, so switching gears before we go to tutorial, I'll probably spend another probably 11, 10, I think. So the theory, yeah.
If you graph like
Mhm.
the non-linear, like what would your conclusion be, or like your interpretation of this data? Like how would you make like, what would you think, how would you?
Yeah. So I would do that ANOVA test with and without the restricted cubic spline. Like I would save both linear model. I would save the linear model and the restricted cubic spline model and compare them using that partial F test. And in this case, they should show massive differences because obviously it's not um obviously it is different. Uh yeah, you can do that. You can do the likelihood ratio test with and without the value as well. I have that in future lecture, likelihood ratio test. But here I would say, what would I do here? I would say we visually inspected the data using both graphs of the residuals and also plots of the fitted versus fit, and also just the X and Y. And the um, assumptions of linear models were violated. So primarily constant returns of the variance, like constant variance of the residuals and homoscedasticity. Therefore, we fit a nonlinear model with a restricted cubic spline with four knots for the variable of x and the outcome of y. And this is just named x and y for whatever reason because it's made up. Actually, recently had one bimodal distribution in the patients taking OAT. They're either really compliant or really non-compliant. They either take their medication or they completely don't, and the in between is flat. So, so you can say, yeah, we therefore fit a nonlinear model, and you can use your partial F test to say that the difference between using a restricted cubic spline and not was statistically significant. In this case, it definitely would be. Um, It's fairly easy to do if you have nonlinearity in your data. A lot of data is linear, but there's a lot of biological sample data that is heavily correlated in nonlinear patterns because of the way that genotypes work. So yeah, it's not much. All you have to do is use this RCS and pick your number of knots. So it's not a huge, yeah,
Even it's like for you add knots to add another turning point.
correct.
You can also use poly. I've used that before. Like
In
y and then tilde poly x and then the degrees. And then the degrees is 3, which makes more intuitive sense.
using the OLS function.
Ellen,
Oh, using LM.
yeah.
Oh, okay. So maybe we should add that to we should add that to.
Yeah.
Okay, so I'll add that later after today. I'll add an LM function as well. I've only used nonlinear in the RMS package, but that's great. That's super helpful. So I'll yeah, keep an eye on that. I'll post it into the modules as well. Any other questions about nonlinearity before we move? Okay. Yeah, and you can also send me a message on Quarkus as well. Okay, so the theory behind sensitivity, specificity, positive and negative predictive value. So briefly, really important, especially for the pathology, also important for embryology and any other thing that you're doing, but really, really important for pathology, like uh, of prime importance, I would say. Every paper, almost every paper will have this. It will try and show you this. And I cannot tell you, there's many papers that are not doing it correctly or interpreting things incorrectly. So the key diagnostic metrics, sensitivity, specificity, positive and negative predictive value. I use a gallbladder polyp diagnosis example in this case. And let me see if I can get my annotation. Ah, it's working. So sensitivity, the ability of a test to correctly identify those with the disease, the true positive rate, mathematically defined as the true positives over the true positives plus the false negatives. So the true positives, those you've correctly identified as positives, and the false negatives, those who are positive but are misidentified as negative. Okay, so false negative, right? It's hard to, it's almost double negative in that case, but specificity. So sensitivity you can think of as, I like to think of it like a net. I'm trying to catch fish in a net. Sensitivity is the total fish in the net, right? So the the narrower the holes in the net are, the more fish you're gonna catch. Like you're gonna catch all of them basically, the small ones, big ones, whatever. Whereas specificity, the ability of the test to correctly identify those without the disease, the true negative rate, mathematically defined as the true negatives over the true negatives plus the false positives. So the patients that are actually negative that you said were positive, and the true negatives in the denominator and the true negatives in the numerator. Now, this is where a lot of people get confused. It's a oh, it's a seesaw. Okay. If sensitivity increases, specificity decreases. And the reverse. They move in exact tandem. An exact seesaw example. It is. Um, I had a disagreement with at a conference with someone about this. They're saying, "Oh no, it is," because if you make the criteria for something, so it's an absolute value. So if I make the criteria of something more permissive, so if I put in more ways for you to get into a definition, the sensitivity will increase. So if I say we just had we're looking at comorbidities for alcoholism, and I looked only at emergency departments and hospitalizations. But then when I added in physician visits, the number of alcoholic uh, the sensitivity of the definition increased. So only 11% of people have alcohol admissions to ED or hospitalization. But once you add in those physician visits for alcohol use disorder, it goes to 66% sensitivity in our population. So for example, as you add more criteria to get into a definition, the sensitivity always increases and specificity will always decrease by an equal amount as well. So it's not possible to have a lot of time people will say, oh, we increased the sensitivity and the specificity didn't decrease. Impossible. Not possible. So again, when you remove criteria for entry into a cohort, the sensitivity will always go down and the specificity will always increase. Okay. Okay. So same thing. So let me just draw the reverse. So if, yeah. So if specificity, so always remember sensitivity, how easy is it to define something? Like how can you get into a cohort? Specificity, how sure are you that the person that you've identified or specificity, how do you know if the person doesn't have what you're looking for? Okay. And it's always a trade-off. Sometimes you may want to capture everyone in the population at the expense of capturing people that may not have what you're looking for. Other times you need to make sure people have exactly what you're looking for at the expense of missing some of the population. So it depends on what you're doing. Depends on what you're doing. Okay. Okay. Now the positive predictive value, the PPV and the MPV. I mean, positive predictive value, the probability. Oh, that's weird. Okay, let me just yeah. The positive predictive value, or the PPV, is the probability that subjects with a positive screening test truly have the disease. Mathematically is defined as the true positive plus over the true positive plus the false positive. Now, notice the difference between the sensitivity and the positive predictive value. This is the key difference, right? They're both the true positive in the numerator, but in the denominator, it's the true positive. The only difference is the sensitivity is over the false negative, and the positive predictive value is over the false positive. Okay. So, given that you had a positive screening test, so the only difference between sensitivity and PPV is they've had a positive screening test. What is the probability that that is a true positive? So there's a difference. So when does this matter? A negative predictive value. The subject with a negative screening test truly don't have the disease. So the practical interpretation for patients, let's just discuss for a minute, and I'll let you go to tutorial. But why does this matter? The difference between PPV and specificity and sensitivity. So there's a gallbladder polyp example posted in the modules. It matters when the disease incidence is rare. Okay. So your sensitivity and specificity may be really good, but for example, if the disease is so rare, like really, really rare, the PPV may be extremely low because it's just not likely to have it in the first place. Okay. So this is really important when you think about the marginal utility of ordering an additional screening test for a disease. So I know recently the guidelines for, I think, mammograms went up in age. And this is kind of the math that they're doing. They found that the PPV at certain ages was so low as to not warrant the additional testing. Okay. So this is kind of, I encourage you to look at that example. I'll probably, when I get the chance, just do like a video explanation of it. But suffice to say, PPV and MPV matter in context of the incidence of the disease. So in a rare disease, the likelihood of the benefit of the test gets lower. Okay. Alrighty. So with that, I'll turn it over to Julia. Everyone get your laptop out and download the tutorial 8 CSV.